But the bosons which sit here together and make it very compact, or it can be a new state of the matter because its density is very high. And it's possible to interpret this state of the matter in terms of some type of the visual particles. So they can be related to the visual particles actually, not real particles. Anyway, so and about the fermion, there is no such phenomena. Fermions are one sit here. If second one sit to here, it should be in the opposite direction of the spin force. Because fermions have different label, They can have the charge, they can have the different charge, and they can have a different spin. Spin is the one which make a difference between the fermions. So, and 2, 2, 2, 2, maximum 2, 2, 2, 2, and 2. Or if you want, it can be one here and one here with the same direction, with same label. For the boson, the situation is very strange. And this is a very interesting subject, actually, Bose-Einstein conversation. And this density, and when happened that the system happened, this phenomena happened when the temperature of the system goes below a critical temperature. So there is a specific critical temperature for any system, which is function of the number of the particle and the mass and these things. And if the system drop below a special temperature, this is a function as well. This is a function of n and m mass of the particle distance. For each system is different. For example, for non-relativistic fermions, this is some equations. For relativistic or ultra-relativistic, for super, everything. Super relativistic, for everything, how you want to think about anything. So that will be different. Even if you have a potential for your boson, so it will be different. For example, this Bose-Einstein condensation can be happen for the vessel of the gas, so in the uniform gravitational field, for example. Just put some gas in the bottle and fall down that in the uniform weak gravitational field near the Earth in the lab. So still this problem will happen, and the critical temperature will be different because of the gravity. So gravity will be affect this also. Normal G, 9.8. Not black person. So there is nothing special about the Maxwell fermion. The only special thing is about the boson. So now I want to go back to the quantum mechanics and explain the difference between the fermion and the bosons. Interchange of the particle will change the system or not. This is the problem. You have two particles, particle 1 and particle 2. And you have two energy state, phi 1 with phi 1 and phi 2, and E2 and E1. The question now is that what is the total wave function of the system? How you can define the total wave function of the system? What is the total state of the system? If this state refers to the energy E1, so psi total for these two particles, x1 and x2, will be just phi1 and x1, phi2 and phi1 and x2. One is referred to energy level E1. Okay. You see that this is referred to energy. If you want to know that what is the wave function for the energy state E2, it will be just phi2 x1, phi2 x2. This index refers to the energy level. This is for bosons, okay? Bosons. Interchange of the particle doesn't change everything. So what does it mean? If you define operators, this operator, I call it P12, the action of the operator is like that. If you acted this operator to anything, just change the order of the functions, order of the particles. This is the act of this operator. Okay? We call it the particle interchange. Particle interchange. So then, for bosons, particle interchange operator doesn't change everything. Bosons are not identified, so they have the same label, so they can change it by each other. As a result of that, they can sit without any problem with each other in the energy state at E1. So both of them can sit here and nothing happen. They don't have any problem. Now I want to back, you know that this interchange or something happened for the system with more than one particle. Just if you have one particle, what's the problem? Nothing. If you have a two or more, it happens. In the statistical physics, you have many, n, no? So I started with. For fermion, situation is very different. They have an exclusion principle. Pauli exclusion principle. Pauli exclusion principle. It doesn't allow the electron to have the same state with the same label and everything. Parity operator over the fermionic wave functions will act with the minus. If you change the electrons, the wave function will be changed for the fermions. Okay, which combination of phi1 and phi2 can give me a wave function which will be with negative eigenvalue of the interchange operators? I mean, how I can write that in terms of the phi1 and phi2. Of course, here you can have particle 1 or 2, any other. Which combination I can write that? The combination should be like that when I write it, and if I change x1 by x2, the total wave function should change to the minus, huh? Total change. It should be something like these multiplied to this minus this multiplied to this or something like that. So this is the way to write it. This Slater operator, Slater determinant. Slater method gives you a way to write the wave function. So this wave function, I write just this, and you don't know that how to write it that, but I give you this. This is the solution for my question. Now tell me that if I change the particle x1 by x2, does the wave function reverse or not? If I change x1 to x2, this row will change to the x to x2. This will be x1, x1. Yeah? Yes? And